announcements too.
So Nick is not here.
Apparently Nicholas is in the country of Europe. So today Yoonsoo will be talking about Shakura Sunyaev disks. Yoonsoo is a second year grad student at Caltech.
Yeah.
Distinguished in spectrum code and other astrophysical phenomena.
Okay.
Take it away, Yoonsoo.
Okay, thanks for introduction. Okay, so today briefly to mention, we have some high energy folks here to attend our journal club over here. So I'm not sure if you guys are familiar enough to astrophysics, but I guess you have like heard of the term accretion disk once in your life, I guess. So, okay. So I think we've been doing some topical reviews or like explain other people what we know for like the past couple of times in our journal club. So I just thought it would be also good to go back to our original intent of journal club, read a paper and introduce it to others. Yep. So I'm going to talk about Shakura Sunyaev disk. So this is actually a paper about accretion disk. It's a model written by Russian astrophysicists Shakura and Sunyaev. Okay. So okay. So first of all, can anyone tell where we can find accretion disk? I think like pretty much everyone knows what accretion disk is, right? So we can see accretion disk from main sequence binaries or AGNs, which are like supermassive black holes. Also, we can see disk in protoplanetary disk, tidal disruption events, which like star passing by the black hole and is perfectly disrupted by the tidal field by black hole. So actually like turns into a disk orbiting that central black hole. And we also expect some sort of accretion disk formed after the merger of like black hole neutron star or neutron star merger. And it's also expected that there can be something like neutron star accretion disk system formed after core quad supernova. Yeah. So this is example image. So left we can see the first image of the black hole from M37. On the right, this is some space telescope picture of protoplanetary disk. So basically, if we want to build a model of accretion disk, we can always start with Newtonian physics, right? If like gravity is not extreme. So we begin with using Newtonian mechanics, but usually it's assumed that the gas is orbiting around the black hole as a free particle, like the point mass, as we learned from orbital mechanics in like second year or third year in undergrad. So this is called the Capillary Orbit, circular orbit like in center petaport balances with gravity. So we can just check this statement. This is usually what is assumed before computing some detail on an accretion disk model. So this is the equation. This is essentially F equals ma for continuum mechanics. So this is just F equals ma for fluid. So on the left you see so that is essentially the acceleration of the fluid element. And on the right you have two forces, for the pressure within the fluid and also the gravity. And if we try to estimate the relative scale of two forces, so first of all we'll start with pressure P equals like number density times Boltzmann constant and temperature. And I'll just roughly say the scale of the pressure variance is about the radius of the accretion disk. The pressure goes to 0 at the boundary of the disk. So it's roughly the scale of the size, the radius of the disk. And the density is number density times mass of the proton. There should be some factor of 2 if the gas is ionized, but whatever. And we have del phi, like a gravitational potential like that. And if we compute the relative importance of these two terms and put some typical numbers we can see from X-ray binaries, this ratio is actually fairly large. So I just here, like 500 is computed from one solar mass accretor, and we say like accretion disk size of like about 100 times short-circuit radius, and temperature is like 10 kilojoule, which is actually very bold assumption. So 10 kilo electron volts of temperature means 10 to the 8 Kelvin. So unless the disk is very, very hot and very, very close to the black hole, we can usually say its motion is usually governed by gravitational force, not the pressure within the disk. So we can conclude that just assuming that the gas is orbiting with the normal like point particle velocity, the Capillary orbit is like a reasonable assumption. And just keep note that in general, like disk usually follows the rotation profile, which is prop to r equals minus the 3/2. Okay, so this is our starting point. And for accretion, we mean the matter falls into the black hole, and that energy is converted to the heat from which the radiation is coming out. We can see, and we call it accretion, right? So for accretion to happen, we need the matter to fall, right? So if it is just orbiting around the black hole like forever, we will not be able to see any radiation coming out from it. So angular momentum of gas should be removed somehow. And for the Capillary orbit, this H stands for specific angular momentum, so angular momentum per mass, which is r squared times omega, which is prop to the square root of the r. And there's an old study called Realty Criterion, which could be obtained by if you study like circular fluid flow and see if like the fluid flow can remain laminar, which is the opposite of turbulent flow. So it just fluid is, you can just roughly understand it as stable. It's just not really precisely stable, but you can just say that if this condition is satisfied, the circular flow is not gonna go to turbulent. And the problem is Capillary disk actually satisfies this condition, right? So you just can't expect how the gas orbiting the black hole loses angular momentum from its state. So one obvious solution we could think of is the usual like viscosity, the friction between molecules. Yeah. But if we put some typical numbers again, it turned out that this time scale is too long, like 10 to the 6 or 8 years. So that essentially we will not be seeing any radiation coming out from black holes that we will actually observe. So this had been a serious problem. So we're seeing accreting black holes, but we don't have a good picture of how it's going to lose angular momentum and fall into the black hole. So there's been a lot of models, and this paper was one of the pioneers that theoretically proposed that, okay, there can be some turbulence, and it would provide some increased amount of viscosity that the time scale is short enough that we can see like days or weeks scale of accretion actually happening, and we can observe the X-ray radiation. So this is the paper. If you want to Google it, you can find this paper here. And if you read the title, it's saying black holes in binary systems and observational appearance. And it should be noted that, so this paper came out in 1973, and the time that astronomers considered that Cygnus X1 might be a black hole was at the same year, 1973. So at that time, we didn't have a really good understanding of how an accreting black hole would look like in the observational sense. Yeah. And I think as far as I searched, the first theoretical prediction that X-ray sources might be the accreting black holes came out, the first theoretical idea came out like 1964 or 65. So this was like the era of like people started to think about theoretically if it is possible that accreting black hole might be emitting X-rays that we're seeing on the sky. Yep.
But so was it understood how like stars accreted today? is something like different about the dynamics of?
Oh, like how star, like you mean like the nuclear reaction? Is that?
So like if you have like a protoplanetary disk or something, right, like presumably this has similar problems with the angular momentum. I mean, maybe the quantities are very different.
Yeah, but like I don't think protoplanetary disks have been observed at this moment.
I see.
Yeah, because it's like more difficult to observe.
But certainly people.
With the aid of like that picture was actually taken by the aid of like space telescope. So.
Yeah, I guess like my question is like theoretically you also would question how any accretion would happen anywhere, right?
Yeah. I mean like, so I think before that people had been studying like when concluding that the sun is like the energy is coming from the nuclear reaction is they also consider like gravitational conjunction, right? But that's like radially fall. And I think like even before this paper came out, there was like a general understanding that some matter coming from companion star should have some amount of angular momentum, not just radially falling into the star. So, as most things in 20th century in astrophysics are, this study began in Russia. So initiated by these two authors, and we usually call it. So, what's the paper is about? I think this is the essence of our journal club today, right? So what the paper tells us. So they're proposing an analytic solution, like analytic model of an accretion disk around a black hole. So that's what it is in the paper. And as you can see from the title, it's like one of the first papers that actually quantitatively predicted the spectra that what we would expect from accreting black hole. And this is a simple model, so there are some assumptions or properties or like the simplifications of pictures. So basically assume stationary state, so all partial key equations go to 0. Also exosymmetry, which might be obvious. And also assume that disk is really thin compared to its like the scale of radius. And it's also optically thick, which means the radiation is balanced with local thermodynamical process. Yeah. Just recall that if for someone who's not really familiar with the optically thin, thick, or opacity stuff, you can see, we can understand like if something is optically thin, if a gas body is optically thin, the radiation just escapes. So it's transparent to radiation. Yeah. But it's like optically thick, the radiation like stays and try to balance with like local thermodynamic equilibrium. This is another detail. And one important clever move this author's made was they actually parameterized how strong a viscosity is by a parameter called alpha here. Yeah. So this paper, the model proposed by this paper is usually called Shakura Sunyaev disk or alpha disk or the standard alpha disk or something. Yeah. All right, so I'll go over derivation. So not like line by line, but like just on a very high level. So how they computed the solution. So basically, they assume that the gas is orbiting around a black hole with capillary and angular frequency, and there's a radial velocity very, very small compared to its orbital velocity. So you can see like gas is basically orbiting around the black hole, but like very slowly drifting into inside, losing their angular momentum. And there's also a corresponding mass influx from somewhere out there, probably from companion stars. Yeah. And it's really common practice in astrophysics, where a lot of disk-like phenomena occurs. It's really common to use this Haight average mass density, usually noted by sigma. Yeah. So first, if we apply the first equation of fluid dynamics, namely the conservation of mass, we can get the obvious result. So like the mass flow should be constant. Yeah. And I will denote as m dot here. And that minus sign stands for because VR is negative, because mass is drifting inward. Yeah. So this is constant and supported by some outer mass flow happening at the outer radius of the companion star. And if we solve momentum equation, which is F equals ma, we can get the formula like this. So this is some kind of relations between the strength of viscosity, the surface density at radius r with some functional form like it. Yeah. And here r0 is a constant, which it actually needs to be specified, where we can roughly just think of as the inner boundary of the disk. And in the paper, it was said to be 6m, which is the last innermost stable circular orbit, yeah, which is a reasonable assumption. And for the strength of viscosity here, mu, so this is where the idea came into. So they parameterized this viscosity with some parameter called alpha, like alpha times CS stands for sound speed, and H is like the scale of height, the effective thickness of the disk. And if you see this equation closely, so first of all, from our microscopic kinetic theory of viscosity, we usually prescribe the value of the mu to be some average velocity of the molecules times the mean free path. And yeah, if you know that, we can just express alphas in terms of namely the ratio of the turbulent velocity divided by sound speed times the length of mean free path divided by the scale height. So this roughly tells us that alpha should be at most about the value of 1. Because, you know, like when we're talking about the molecules like going up and down, the mean free path cannot be longer than the height of the disk itself, right? It's bounded. Yeah. And also, if the speed is, like say, the speed relevant to viscosity is larger than the sound speed, it would make a shock wave, which will like dissipate the heat really faster, and just velocity actually drops below the sound speed. So this alpha is a parameter bounded by a value of roughly 1. In actual situations, like numerical simulations, people can actually confirm that this falls within like 10 to the minus 3 or like 10 to the minus 1. Yeah. And we have a last piece in the energy equation. So here Q is the heat generated by viscosity between each rings. So this is the heating rate at the radius r. And if we equate this quantity with some expression of radiation, let's say like sigma t, like t to the 4 or something, based on what kind of state the matter has, it will give us some relations on thermodynamic quantities at that point.
So the fact that the m dot is constant, that's like a requirement you're putting on the system. It's not like an ansatz.
It's a requirement. Yeah, I'll just call it, I forgot what we call it in physics, like first integral. Yeah, so like one of the parameters that we can label models. So this is the plot of here, the heating rate Q over radius R. This is figured from the paper. So you can see that most of the heat are coming from the inner part of the disk, and this gets like cooler if we go to outside. Yeah. So the QR is just the value of the heating rate, and the reason why we have another plot, QR times R squared, is that's the actually the integrand that comes in if we trying to compute luminosity by integrating the heating rate. So you'll see the maximum occurs about to like 2.25 times the innermost radius of the disk. So I'll just skip all the steps and just give you the solutions. So it depends on, okay, so I'll ask you guys. So what's the relation connecting pressure and energy density? Yeah, the equation of state. And we haven't said anything about the equation of state, right? So it depends on how matter and radiation is mixed. Okay, so first of all, so they divide the whole region into A, B, C, like 3 types of regimes. So first one is for radiation pressure dominant. So which is like radiation pressure is much larger than the pressure made by matter. Okay. So maybe like P equals energy density divided by 3. I think that was the formula. Yeah. So if we assume that, and also assume most of the opacity is coming from the scattering by electrons, we get this simple solution. Well, it's not really complex. It's still a rational function, right? So these are all the units, dependencies. Another regime is the matter pressure is dominant, but still opacity is dominant by electron scattering. You'll see this kind of solution. To see that how simple these solutions are, it's just like some value times some scaling of alpha, m dot, and m. Yeah. And the RAB means just roughly the transition radius between region A and region B. Yep. So that like the matter pressure gets comparably same as the radiation pressure.
Wait, sorry, what's R? It's like the distance to the.
Yeah, it's like R over like large R over large R0, so it's like some dimensionally standard. Yeah. Also M and M dot, yeah, so it's some kind of like dimensionless numbers proportional to M, the actual M and M dot. Yeah. The part C solution is for matter pressure dominant, and also opacity was coming from free interactions, which we call breaking radiation or Bremsstrahlung. We learned from A125. I don't remember, but so these are the formulas, the solutions, and also the transition radius. And if you look at this kind of all the solution, and especially for where the transition occurs, so like where marks the okay, this is a part of the accretion disk that is like a little bit different from that. And we can actually check that this really doesn't depend on alpha and m. So like exponent is not the b, but mostly dependent on m dot accretion rate. Yeah. In which I think we can check again that the grand principle in astronomy that most of the things relevant to everything is in astronomy is usually mass. Yeah. So you will see that most of the solution, like all of the solution, only depends on 3 parameters: the mass of the accretor, the alpha, and the accreting rate m dot, which is set to be constant. So for a fixed accretor, like the whole picture of accretion disk is determined by these 2 parameters. Yeah. So like how large is the mass inflow, and how large is the viscosity inside of the disk. So let's see. So here we see transition radius is like depends on the base accretion rate, right? So if that means, let's say we have a black hole here, region C, B, then let's say region C, and if accretion rates, the mass inflow from companion like increases or decreases a lot, it means that this layer can actually change over time, which can also explain the different character of radiation it's emitting depending on how much mass is coming from the companion star, which is remarkable. So this is a plot from the paper, which is plotting the temperature over some different values of alpha, and the x-axis is the mass accretion rate. And that over m dot cr, you can see on the right bottom, that's the Eddington accretion rate. So we can just check that at most that this is about hot as like 10 to the 8 Kelvin. So, and this is another plot from the paper, which plotted the temperature along the radius, and also for some different values of alpha and m dot over here. Yeah. So I tried to understand this figure for a long time, but I think there's like too much astrophysics going on here. Okay.
What is that R variable?
Here it is.
Yeah.
R divided, I think that should be 3R0.
Okay.
Yeah. And yeah, there are actually some typos in this paper. So if you look at solution T on the region C, there's a Z, right? That's R. Right. That should be R. Classic old papers. So this is another plot from the paper. It comes out some like first chapter, like overview section. So this is the true results. So this is the expected spectra over frequency of an accreting black hole. So we can call it as their like final expectation that we can observe from accreting black hole. Yeah, and you can see like most of like the strength of the spectra mostly depends on accretion rate. Like some detailed structure depends on the value of alpha. Yeah, I like these like 40 years old style of figures, like, not like contemporary one, just black and white. So these are the pictures of these two authors. So left is Nikolai Shakura, on the right we see Sunyaev. So this is the picture about 40 years ago, after they published their results. So you can see some like familiar formulas behind them on the chalkboard. And I guess this picture is like less than 10 years before, like less than 10 years ago. So after they got some prize from some physics institution. So, yeah. So they wrote that like famous formula alpha equals something on the chalkboard. I didn't know both of two were like still alive. Yeah. You'll see. I actually saw like last month some archive article in which like their name was yeah. So like Shakura and Sunyaev still giving their authorship on papers. So just stay tuned. Okay, so one key question that was unanswered in this paper was, so they parameterize viscosity in terms of alpha, but that doesn't really tell about which physical mechanism is responsible for generating that viscosity. Yeah. What they provided was, okay, let's say viscosity is like strong with the alpha or something. So actually, so this is like after story of this paper. So what actually drives turbulence in the disk? What physical mechanism drives it? And again, I found an advice from one of undergraduate advisors useful again. So what he used to tell in introductory astronomy class for freshman students is, if there's something really weird happening in astronomy, it's usually because of magnetic field. Okay, this would sound funny. Yeah, I wish there was like an astroclass student here anyway. This is usually true. Okay. So there's an instability named magneto-rotational instability, which usually called MRI. Yeah. I think that's like the second correct MRI, like second term MRI comes out if I just type MRI on Google. I think the first one is like the one used in hospital. So, so this mechanism was actually studied long ago, like 1960s, but its practical application in astrophysical context had been revisited in 1991. This is a really famous paper, like cited numerous times, Douglas and Hilley. So if we have a rotating disk threaded with some magnetic field, some mixed effects of this rotation and magnetic tension force induces instabilities on rotating fluid. And the condition to trigger this instability is it's just angular velocity decreasing over radius. This is really it's very, very common in astrophysical disks. Yeah. So it's kind of like ubiquitous mechanism to drive instabilities on astrophysical disks. So it's basically everywhere. And one powerful thing about this instability is it's even sensitive to very, very weak magnetic field. So if magnetic field is really weak, instabilities will start developing the turbulence from, let's say, very high wave number, yeah. But eventually, after some time scale, it will eventually grow up to the scale large enough to drive actual macroscopic instabilities on the disk. This is very important mechanism to drive turbulences in the real world astrophysical disk. This is not the only one. So we have, if you look at the reviews on the papers, the self-gravity of the disk can also trigger some kind of instability. And there are all the other effects, but I'll say this is pretty much like dominant in usual situations. And also this is the effect that our code is trying to resolve with the minimal number of grid points. Yeah. Because whatever grid resolution you will have, there is always MRI developing on a smaller scale rather than the grid resolution. Yeah. So like this plot, this really active area about how we can correctly capture like as much features as possible with the limited number of grid points or computational resources. But this is not the end of their alpha disk model. So let's say we added some kind of very complex physical mechanism like MRI or some instability, like some new instabilities in like 30 years. That can be actually interpreted into, okay, so this actually corresponds to effectively alpha equals some value. So if like say actual numericals like 3D simulation may be like too expensive, or if you try to build some disk model analytically, we can just say, okay, I'll include these effects which correspond to alpha, effectively alpha equals some value, then just move their alpha models. Okay. So the alpha disk model is like quite old. It's like paper came out 50 years ago, but still finds an application today as well, which I think really remarkable. It's really hard that some crude model is still used with some like a little bit of modification. So I will say their parameterization of viscosity effect with alpha was a very clever choice. And this is the plot, the metric that you can actually see on the NASA ADS system if you search this paper. And pretty much every paper doing accretion disk physics might be citing this paper. So there's a review paper talking about this graph, and the citation number of this paper can be actually used as a metric to like quantify how active this field is. So from this plot, roughly the exponential increase, we can just say the field of black hole accretion physics is expanding. Yeah, and the last one is like this year's citation, so it's still going up. Okay, so it's not particularly long, but I'll just say that this paper is a really seminal paper in the accretion disk community, and it's still used today. So like their approach was very clever, and the personal impression that I got from this paper is it's really concise. So we need a lot of knowledge, not just in gravity or fluid dynamics, but like radiative transfers or like in general astral context. So it was really fun. I had really fun time to read this paper, though I couldn't read all of it. Yeah. So if you meet the term alpha disk or alpha prescription of viscosity, or like there are actually some papers just telling this model standard accretion disk model without like referring like alphas or their names. So if you meet the term like that, you can just think, okay, that's talking about the Shakura Sunyaev model that came out 50 years ago. Yeah, that's all I prepared for today. I'll take any questions.
So how good like in practice is the constant like mass flow rate approximation? Is there like any limitation, or is it just like, you know, time scale of the mass at like m dot changing is so long that it's irrelevant?
I haven't included the figures, but I've read that there has been some observational studies that actually got this observational data and tried to fit that data with their predictions. And I think the result